A firm manufactures a commodity at two different factories, Factory X and Factory Y. The total cost in dollars of manufacturing depends on the quantities X and Y produced at each factory and is given by C of X, Y. If the company's objective is to produce 1,900 units per month while minimizing the total monthly cost of production, how many units should be produced at each factory? And then for this combination of units, what is the minimum cost? So we want to minimize our cost function C of X, Y, given the constraint that the production must be 1,900 units, which means X plus Y must equal 1,900. We're going to solve this using the method of Lagrange multipliers, where if we're trying to maximize or minimize the function f of x, y under the constraint of g of x, y, then the gradient of f must be equal to some multiple of the gradient of g, meaning the gradient of f is equal to some constant lambda times the gradient of g. The components of these two vectors give us the first two equations. The third equation is from the constraint. So because our constraint is x plus y equals 1,900, we're going to use the function g of x, y equals x plus y minus 1,900. Let's set up our system of equations on the next slide. So for our first equation, we'll have the partial of c with respect to x equals lambda times the partial of g with respect to x. So the partial of c with respect to x would be 2x plus y, because we're differentiating with respect to x, treating y as a constant. We have equals lambda times the partial of g with respect to x, notice how it would just be 1. So we can leave this as lambda. For our second equation, we're going to have the partial of c with respect to y, which would be x plus 4y equals lambda times the partial of g with respect to y, which would also be 1. And our last equation is g of x, y equals 0, which would be x plus y minus 1,900 equals 0. Notice how our first two equations are already solved for lambda, so they're both equal to lambda, then it must be true that 2x plus y must equal x plus 4y. And now if we solve this equation for x or y, we can then perform substitution into the constraint to form an equation with one variable. Let's go ahead and subtract x on both sides and also subtract y on both sides. Notice how this would give us x equals 3y. So now that we know that x must equal 3y, we'll substitute 3y for x in our constraint, then solve for y. Let's go ahead and do this on the next slide. Using the constraint x plus y minus 1,900 equals 0, and x equals 3y, performing substitution, we'd have 3y plus y equals 1,900. So we have 4y equals 1,900. Dividing both sides by 4, we have y equals 475. Well, now that we know y equals 475, we also know x equals 3y. X must equal 3 times 475, which is equal to 1,425. So this is the x and y value that minimizes the cost function. So going back to our question, factory X should produce 1,425 units, and factory Y should produce 475 units. Now you might be asking, how do we know this is a minimum cost, not a maximum cost? Well, if we take a look at our function c of x, y, notice as x and y increase, the cost is also going to increase. But if we wanted to check this, we could select another x and y value that satisfies the constraint and see what the cost would be. But let's first answer part B by determining the cost at this production level, which means we want to determine c of 1,425, 475. Let's go ahead and do this first. So c of 1,425, 475 comes out to 3,158,950. This would be dollars. And again, just to select another point that would satisfy the constraint, let's go ahead and evaluate the cost function at c of 1,000, 900. This actually comes out to 3,520,200. So this is going to be the minimum cost given the constraint. So going back to our question, for part B, we have $3,158,950 as the minimum cost per month. Now before we go, let's take a look at the graph of the level curves of c of x comma y and g of x comma y, just to see that their gradients are multiples of one another at this point. So the level curves of c of x comma y are graphed in blue, and the level curves for g of x comma y is graphed here in green. This is the point 1,425, 475. These two vectors are the gradients. They're actually multiples of the gradient, so it looks nice on the graph. But notice how we can see they are perpendicular or orthogonal to both level curves at that point, and they're also multiples of one another. So this is where we have the minimum cost function value. I hope you found this helpful.